Greetings to everyone. Welcome to the second day of our national webinar on chromatography, multifaceted analytical techniques. It's wonderful to have all of you with us today. I again extend my greetings to everyone and further welcome to our chairman, Sir, Shri Kapil Singh Ji M. Chauhan, our secretary, Shri Devdas Shah, Sir, our treasurer, Shri Vishwesh Dave, the members of our trust, our resource person, Dr. Deepak R. Thakur, Director of ACRNS Technologies Private Limited, and our valuable delegates who have joined us from far and near. Yesterday we had a wonderful session in which Sir brought us to understand various aspects of the properties of the packaged materials of columns and how we can have eco-friendly systems which give us good resolution and wonderful results. Without taking any much time of yours, I would request Deepak sir to take on today's session, which is planned on applications and studies of liquid chromatography in pharmaceutical and biopharmaceutical industries. Over to you, Deepak sir. Good morning and all the best.
Good morning, everyone. Am I audible, madam?
Yes, sir, you're audible.
Okay. So,
Sir,
how many participants we have today?
I'll just check out the exact number, sir.
Okay. So, welcome to everyone. And I'll just give some brief background about yesterday's presentation for those who are joining first time today for the second session. We yesterday spoke about chromatography, how the invention of column chromatography happened, what are the basic principles involved in chromatographic separation, and after that we looked at different components involved in HPLC machine, what are their roles, right from solvent reservoir to degasser to pumps, then injector, column, and detector. Among these components, column plays a very important role as it is called as heart of HPLC, where separation of components of a sample, different analytes which are present in the sample, separation of those components happen in column. Currently, in pharmaceutical or biopharmaceutical industry, the columns which are used at a flow rate of hundreds of microliters to milliliter, these are the flow rates used, and the columns which are used have packing material, that is silica particles, spherical silica particles ranging in their diameter from 1.7 to 5 micron. This is what usually chromatographers in industry are using. However, the trend is towards miniaturization. That is, how can we miniaturize and benefit? What are the benefits of miniaturization? So yesterday we looked at the construction, how these miniaturized columns, which are, whether these are nanoparticles based columns or micro pack column, which are micro pillar array columns. So to start with, I'm going to mention that what we are going to discuss today. So outline of this today's session is, again, I'm going to go over the features of micro pillar array columns, and this is going to help those who are joining today. Then we'll be looking at introduction to metabolites profiling. What is the role of metabolites profiling? How that's useful? That's what we are going to see. Then we are going to see the challenges with respect to nature of sample and the role of liquid chromatography. And as it becomes nano, the detector use is mass spectrometry. We are going to see the benefit of nano LC connected to mass spectrometry, especially in analysis of metabolites, also in the analysis of proteomics. this it plays a great role. And what are the features which help you identify low abundant metabolites, co- metabolites which are low abundant, the whole profile which is complex, how nano LC connected to mass spec helps us in deciphering the content of the metabolites. And we'll look at case study, and during the case study we'll look at how the use of micropillar array column helps in identifying relatively more number of features in metabolite profile. So to start with, and yesterday I showed this slide to you, that is, what are the advances in column packaging, and what do you mean by the packing of these particles or packing of micropillar array in a column. So if you see closely on the left, on this side, if you see this one, these are all arrays of micropillars, and these are the pillars which are generated from a silicon wafer. It's just the height of these pillars is 18 micron, 1/8, and the diameter of this pillar is 5 micron. The space between the two pillars is 2.5 micron. And if you see, the outer surface of this pillar is porous. Porosity is 30 nanometers, and the edge is only porous, not the central part. And that is, the porosity is up to 300 nanometers. And see the uniformity of the pillars formed. This uniformity is the cause of better performance of this column. If you see on the right hand side, is thousands of years before in uh, Ajanta caves, these type of structures were carved out of monolith. Big mountain was carved. And how did they start their work? Not from the bottom. It was from the top. They started from the top and then they keep doing it. See this pillar, it was started from the top. That means this particular um, idol which is placed here is carved first, and then they move down. Usually we do that from bottom up, right? But here this is carved from top to bottom. And this is the same way these pillars were generated in a silicon wafer using dry etching technology. So columns are formed by carefully etching a solid silicon wafer to create separation beds of highly ordered arrays of freestanding pillars. So as I mentioned, these pillars are just 18 micron high and 5 micron in diameter. The spacing between them is 2.5 micron. So what are the advantages of micropillar array columns? They provide you miniaturization. What is the benefit of miniaturization? The flow rate is in nanoliters, 250 nanoliters. Think about it. Even if you run for whole day or a week, what will be the consumption of solvents? And this miniaturization not only saves solvents, but it saves samples, because you need almost 1,000 times less amount of sample to analyze. So the benefit is you save sample, or in other way around, those samples which are very limited in small amounts, on them you can do this analysis using these columns. Second thing is, because the pillars were generated using a very reproducible procedure, there is a uniformity in the whole column construction, and that helps in giving you a consistent performance. What do I mean by consistent performance? The retention times are consistent, the peak shapes are consistent, and that helps in comparing different samples. That helps in comparing results developed yesterday with the results developed today. So this helps in better comparison and sensitivity, because these columns function better at lower flow rates. When we connect these columns to mass spectrometry, the benefit is, I'm going to show you that how use of LCMS with, or use of these columns in LCMS helps in increased sensitivity. So you are already working on trace amount of sample, and even in that, you can look at the low abundant compounds. That's the benefit. The sensitivity is high here. So the advantages of micropack columns are extreme robustness, increased column to column reproducibility, high flow rate, flexibility. The beauty is the optimum flow rate is 250 nanoliters, but because these columns have low back pressure, you can go up to 1.5 microliters per minute. So that's the flexibility you have. You can go from nanoliters to microliters. Then it provides optimum separation performance, because you can run longer gradients on these columns. You are not only separating many compounds, but you are going deep. In presence of abundant compounds, you are looking at trace amount of compounds. So therefore, what is the benefit? Improved coverage. You are not only covering most abundant components of the sample, but you are covering the low abundant components of the sample. So as I mentioned, the application, one of the application we are going to discuss of use of LCMS platform comprising of micropack column is metabolomics. So bolomics, if you see omics, you must have heard of genomics, transcriptomics, proteomics, metabolomics, glycomics, lipidomics, right? So when you study lipids, it's lipidomics. And when you look at metabolites, you look at metabolites in a complex sample. When you look at proteins in tissues and blood samples, and you compare them between healthy people and diseased people, why do you do that comparison? To find out the biomarkers which are indicator of disease. You want to search those biomarkers, and those biomarkers are indicator. We can target them for drug discovery. We can use them, these biomarkers we can use for diagnostic purpose. So there are many applications of these omic study. So metabolites profiling is the measurement of low molecular weight metabolites and their intermediates in biological system that reflects the dynamics response to genetic modification, physiological, pathophysiological, and development stimuli. So the goal is to acquire profound insights into biochemistry of an organism at a certain moment by identifying endo and exogenous metabolites present in the extract of biological tissue or biofluids. This is what the general metabolite profiling workflow is. First thing is extraction of metabolites. And what you have to do, you have to use right type of solvents. The metabolites are vitamins, they are lipids, they are small molecule organic compounds, water soluble compounds, they are, as I said, amino acids. So these are falling under the category of metabolites. So if you get a tissue sample, you'll have to solubilize the tissue, use methanol, chloroform methanol combinations to extract metabolites from there. And what you need to do is add internal standard. Why do we add internal standard? To ensure that our recoveries are consistent during the sample preparation. Internal standard helps us in demonstration of consistent recovery. Not only that, but they also help you in quantitation. So I'm going to show that here in the next part. If you see, for once you generate these samples, you prepare samples of metabolite. This extract you load on UHPLC MS platform. Mass spectrometry provides you a additional dimension of separation. So if you see, I'll just draw here, I'll draw a chromatogram. Today, the pen is not accessible to me. I'm just wondering why it is so. Only laser pointer is accessible. So I'll show you. If you see this chromatogram, what you see is on the x-axis is time, and on y-axis is the intensity. But at every moment, the mass spectrometer is profiling the content and is plotting the content it sees. And how it's plotting intensity versus mass to charge ratio. So the compounds which are eluting in this peak, if there are multiple compounds, can be hundreds of compounds, mass spectrometer separates them because they have different mass to charge ratio. So the role of HPLC or separation column connected with mass spectrometry provides two dimensions of separation. See here the role of internal standard. Internal standard helps you in quantitation because we know what is the quantity of internal standard added, and that helps us calculate the amount of metabolites and what is their concentration in the sample. Then you have to do statistical analysis that if the extract is taken from a healthy sample versus diseased sample, the sample which is taken from a deceased person, when you compare it, you want to find out what are the differences in the level of metabolites. Because in case of deceased person, the metabolite consumption increases, so therefore more metabolites are produced. And you see that if you profile the blood for vitamins and other type of metabolites, you will find that in disease case, in case of disease person, his sample is showing that there is an increased level of metabolites. So that, and what you consider as increased level, twofold, threefold, fourfold, that is called as statistical analysis. And based on statistically significant increase in the level of amino acids, in the level of lipids, in the level of organic, water soluble organic compounds, based on that, we identify biomarkers. We say that yes, between the normal tissue or normal person and his blood sample against the cancerous person, his blood sample, we see some differences, significant differences in the profiling of metabolites, and those metabolites which are significantly different are identified as biomarkers. So this is what the circle is of metabolite profiling. Moving on, what are the challenges with the samples? If you take two patients having similar type of, or even healthy people, they have different eating habits. What they eat, how they eat, when they eat has a role to play on our metabolite profiling. So these are the challenges. You cannot decide what is the healthy levels. What about trace amount of components? And there are techniques like laser capture microdissection. You can separate one cell from the tissue and do the analysis. So that is done using the laser capture, provides few cells. And this is useful when the cancer or any disease is at initial levels. In initial levels, only few cells are present which are cancerous. But because we want to treat a person at early stage, we need to study it. And these type of samples are present in trace amounts. Again, if you see tissue samples, the number of metabolites present, if you see blood samples, the number of metabolites present, whole the complexity is very high. Not only complexity in numbers, but their concentrations. Some of them are in ppm level, some of them are ppb level, some of them are in percentage. You need to analyze them together. And these samples, especially early stage samples, are rare. So these are the challenges with respect to sample, and how liquid chromatography can help to solve these challenges. And this is what today, through the example I'm going to show you, that the role of liquid chromatography helps in handling the complexity and low concentration range of some of the metabolites. So powerful analytical techniques with increased sensitivity is important. Nano LC columns, which are right now packed columns, packed with the beads, are being used for this particular purpose. They provide unprecedented separation efficiency and minimum peak dispersion. The liquid chromatography can be connected, coupled with mass spectrometry. As I said, it provides another dimension of separation, and it's a very sensitive detector. Mass spectrometry is the most sensitive detector. Combination of superior separation performance and increased detection sensitivity enables identification of even more and more components. What I see is, and what I'm going to show you is, that even though nano columns with particles are currently the state of the art columns available to us, even these columns are not sufficient to provide, to cover all those metabolites which are present. So the next advance in chromatography is micropillar array chromatography, which you have seen the design, and I'm going to show you the data, and I'm going to justify that how it's better than the current state of the art columns available to us. So first, so the case study which I'm going to talk to is analytical performance of micropillar array column for metabolic profiling, and the samples which were taken were from poplar bark tree tissue and Arabidopsis tissue. So one is tree, another is plant. And the tissues of these plants were taken, and plant and tree were taken, and they were extracted with methanol. Then the supernatant, that means the extract, was dry freezed and redissolved in water and cyclohexane 1:1 ratio. Many times this is done to get lipids out away from that of water soluble metabolites. And why these two examples are taken? It was known that these trees and plants have capability, they have metabolites which fight against the infection due to insects, the attack of insects on these trees. So the case study which we have taken from a paper, published paper, the goal was to look at what type of metabolites they have, and what is their role in preventing infection due to insects. So we are using this case study to demonstrate how micropack column, micropillar array column helps in metabolomic profiling. First, we'll look at what are the differences in current state of the art conditions, which are on the right hand side, and nano LC conditions, especially when we use micro pack column. If you see, you need a nano flow LC. Nano flow LC means the flow rate should be right from 100 nanoliters or below to microliters. This should be the range. And here, as I mentioned yesterday, that the column, micropack column, is just a credit card size column, very thin and only a credit card size. But inside there are grooves, and these grooves are multiple grooves there, multiple parallel rows of these columns or these pillars. And what is the length of the column inside? 200 centimeter. So think about it. Such a long length of the column is packed in just a chip, that is credit card size chip. Mobile phase, usually when you do LCMS work, you do not use salts because they are deleterious. They are not compatible with that of LCMS activities. So the mobile phase is water acetonitrile composition with formic acid, 0.1% formic acid. If you see the flow rates which are used, they are in the range of 300 nanoliters or below that to 1 microliter. And different gradients are used. If you see the the percentage B, that is acetonitrile content, is changed during the gradient from 1 to 50%. So it is 80% acetonitrile, which is solvent B, which is changed from 1 to 50%. And what is the different durations which were tried? Something like 30 minutes, 60 minutes, 120 minutes, 180 minutes, 30 minutes, 300 minutes, and 420 minutes. You must be wondering, why 420 minutes? Why such a long gradient? Most of our runs are and our are maximum 30 minutes or maximum 90 minutes for very complex samples in pharmaceutical industry. But if you go for such a long run here, you provide opportunity for low abundant components to be detected in presence of high abundant components. Whereas if you see on the right hand side, this is again a nano HPLC which is performed with the columns which are packed in 2.1 mm. 2.1 mm is 2000 micrometers, right? And here it was something like 60 nanometers or 60 micrometers. So if you see here, the column, micropack column, its inner diameter was around 60 micrometers, whereas it is 2000 micrometers. So think about it. The column dimensions are different. The construction is different, and that helps you in running low volume samples, running very precious samples at the cost of, there is no cost, but there is a benefit, and the benefit is low abundant compounds. You do not lose anything, but you gain, though you are using low volumes. So see here, for this dimension column, the flow rate is 300 microliters, whereas the flow here is 300 nanoliters, almost 1,000 times saving on the solvents. Again, at such a flow rates, the preferred maximum run time is 180 minutes. So, especially in on both the systems, poplar bark metabolite extracts were run and compared, whereas additional sample of Arabidopsis leaf metabolites were run and demonstrated on micropack column based chromatography. Think about it. What is the injection volume? 4 nanoliters. So if you have really limited samples, you can really work on it. And the injection volume here is 5 microliters. So it the availability of micro pack column enables trace analysis, components which are in trace amounts, and components which are in the higher abundance, you can use them in minimum quantity. Now I come to nano ESI and normal ESI. And I'm going to show this because this is very important. This electrospray ionization. So when you separate compounds on chromatography, the liquid is eluting out of the column, is going to detector, and then it comes out. And when it comes out, it is sprayed in the mass spectrometer. The benefit of flow rates, what is the benefit of lower flow rates? I'm going to show you here, but before that, I want to explain you conditions. What are the differences? Think about it. The nano electrospray and the difference between nano electrospray and normal electrospray. Electrospray ionization, I'm going to explain it to you in the next slide, but just see the voltage required for spray is 2 kilovolts, 5 kilovolts. Capillary temperature is 200, here 275. Additionally, you need gases. You need gases, that is nitrogen gas. And what is the role of it? I'll show you in the next slide. So here, the process of ionization. Mass spectrometry needs ions in gas phase. And the molecules which are getting separated, the metabolites which are getting separated in chromatography are in the liquid state. So when we separate them, they may be charged, they may not be charged. And mass spectrometry measures molecules in terms of their mass to charge ratio. If there is no charge, the masses, neutral masses cannot be measured. So one of the requirement is to generate ions, molecules, whether they are in ionic state or they are neutral state in the liquid phase, needs to be converted into gaseous ions so that mass spectrometry can measure it. So let's look at this particular picture on the left hand side. What you do is, this is a nano spray and you apply voltage to it and you have mass spectrometer here. What happens in conventional electrospray ionization? In chromatography, these molecules are separated. The separated molecules come out of the capillary column, and then there is a tubing connected to it. Through it, it is connected to capillary, a metal tip. Through them, they come out. And what happens when you apply voltage to this metal tip? The droplets are generated. These droplets, with application of gas here, there is a concentric chamber or cylinder around this, which through which gas comes out, which helps in evaporation of solvent. As solvent evaporates, the size of droplet decreases, and when it becomes smaller, the charges inside these droplets, they repel each other and there is a Coulombic explosion. That means the same charges are repelling each other because the droplets are becoming smaller and smaller. Many charges are compressed in the small volume and they undergo Coulombic explosion. This Coulombic explosion causes release of ions, and these ions enter into the mass spec. Now think about it. If your flow rate is higher, like ml or 300 microliters, you need gas because droplets are bigger, and you have responsibility of evaporating all the solvents so that ions will be generated. But think about when your flow is in nanoliters, the droplets will be very small, already very small. You don't need gas. They are already very small. And through Coulombic explosion, the ions are generated and they enter the mass spectrum. See, this particular picture on the right hand side, here is a tip. This is a tip through which liquid is coming out, eluent is coming out, the voltage is applied here, and this type of spray is formed. Think about it, this spray has all the droplets. And this is how it looks like. When you do LCMS, you will, if you see it under the microscope, you will see it like this. And there are fine droplets. Think about it, if your flow rate is low, they are already low in size, evaporate, and the efficiency of ion generation is very high. So if your sample is low, already your sample is very less, that sample has opportunity to enter into the mass spec. But here there are chances because some droplets may remain, big droplets fall down, they may not evaporate, and therefore the efficiency is a problem here. But it's not a problem with nano spray tips and nano flow based electrosprays. So I hope you understand that the electrospray ionization, which is causing a spray by application of electric field or electricity, you're applying voltage to the tip and causing spray to happen. This particular nano spray, which happens for a nano flow, doesn't need any gas. So efficiency is really high here. I'm going to talk about another concept, which is peak capacity. What is peak capacity? Peak capacity is a measure of number of peaks that can be resolved in a specific retention window. Suppose you are running a gradient between 5th minute and 90th minute, 90. So the window is 85 minutes. And in this window, how many number of peaks you can separate? And who decides this? Who decides that how many numbers of peaks are present in this window? The width of that peak. So the formula for formula for peak capacity is the time duration in which gradient is running, the time duration in which the first peak and the last component of the sample is eluting, divided by width at 13% height. So your peak, if your peak is like this, if that's a peak, the total height of the peak is 100%, assume that's 100%. So from bottom, approximately 13% height, what is the width of the peak? So that peak, if that is 1 minute, so in 90 minutes, you have 90 peaks. That's a 90 is the peak capacity, right? The beauty of this particular micropack column is the peak width is in the range of 20 seconds. So per minute, 5 peaks can be accommodated. And if your runtime is 400 minutes, think about it, how many 2000 peaks you can have a peak capacity of 2000. And think about it, if 2000 peaks you can separate, under each peak, if you have multiple compounds, mass spectrometry has capability to separate thousands of compounds. So multiply 2000 by another 1000 or 2000. Think about it, how many compounds you can analyze using nano LC connected to mass spectrometry. I hope you are getting this, what I'm talking about. So here we see how that chromatogram looks like. This is a chromatogram which we see using micropack nano LC column. This is again a nano column, but this time this column is packed with beads, 1.7 micron beads. And if you see, If you see here, see the shape of peaks. These are the most abundant compounds. See how big these peaks are. One, two, three. These are the most very abundant molecules in percentages. And think about it. There are these compounds, which are low abundant compounds, right? The difference you see here is this is a micropack column, and see in noise level, see here, these are the packed column and you don't see it. And again, both of these are the packed columns and there is no consistency, right? These are eluting here, in another column they are eluting here. So there is no consistency in nano columns packed with beads. But when you look at micro pack column, see the number of peaks you are seeing. There are additional peaks, and these are the peaks. This is called as base peak chromatogram. When you run chromatography connected to mass spectrometry, what you get is the different type of chromatograms: total ion chromatogram, base peak chromatogram, extracted ion chromatograms, different type of chromatograms. And what do I mean by these chromatograms? The first one is total ion chromatogram. Everything, whatever you see, everything is added up and you see the signal. Base peak, when the spectra is taken, the most abundant peak is its intensity is taken and is plotted. So here, only the most abundant compounds in a spectrum are plotted. But in the spectrum, there are so many more compounds, metabolites present, which are low in abundance. So a lot of information you get. What I'm trying to show you here is, even with the 1,000 times low injection volume, here it is 4 nanoliters, here it is 4 microliters, 1,000 times less amount of sample, and still you get 30% more distinct features. What do I mean by distinct features? These were not seen in this LCMS analysis. 30% low abundant compounds were seen, measured, and can be quantitated using micropack based column connected to mass spectrometry. In this particular comparison, what we are showing is the peak shape. No doubt, even these peaks are better compared to your conventional chromatography, which you perform at higher microliters to ml range. Compared to them, these peaks, which are generated from packed column packs with the spherical beads, these are much better. But further improvement is provided by micropack column. See the shape of these micropack based peaks compared to columns packed with the beads. So in and another benefit is increased ionization. I showed you the electrospray ionization. It is so beneficial that you save on gas. You don't need gas to evaporate solvents from the droplets, and everything is ionized. Nothing is lost. Whatever is separated, whatever is loaded on chromatography, whatever is separated and eluted from the chromatography, everything is entering inside the mass spectrometer. The efficiency of transfer of ions is very high, and because of this, detection sensitivity is also high. What we see here is, again, microfluidics is the company which has invented this column and brought it to the market. Not only invented, many people have worked on these type of columns, but commercialization of these columns and making them feasible in any lab is a great task which they have achieved. So microfluidics is a company which has commercialized this particular column, and you see the performance, the intensity on the right hand side, e raised to 6 compared to here, e raised to 5, isn't it? See, the width of the column is 0.11 minute at half height. That means what is 0.11 minute? Around zero point 0.6. So around 6 to 9 seconds. So if 6 to 9 seconds is my width, how many peaks will be there per minute? 10 peaks. And if my runtime is 300 minutes, for example, 300 into 10, think about it. 3000 peaks I can separate, and these 3000 peaks further will be separated in the mass spectrometer. So huge contribution towards increasing the coverage of metabolites you cover. See, in case of state of art column, it is still double of this. So the peak capacity, we saw the formula, which depends upon the width, will be half for these columns, which are packed columns. Now, here what we are looking at is the effect of increase in gradient time. So if you see, the gradient times are increased from 30 minutes to 60 minutes to 120 minutes to 180 minutes, right? And at different run times, is there an impact? If I run the gradient for yesterday, I spoke about Vam-Dimter equation. Vam-Dimter equation, where I spoke about three parameters: A, B, C, eddy diffusion, longitudinal diffusion, and mass transfer. The moment we run a longer gradient, there are always chances of diffusion, the peak becoming wider. If peak becomes wider, if its width increases, what will be the problem? The number of the peak capacity, the number of peaks which can be accommodated in this separation will be low. But if you see, because of this unique construction based on pillar array columns, that arrangement of pillars, even if you move from 30 minutes to 60 minutes to 120 minutes to 180 minutes, if you see the width, it is moving from 0.16 to 0.10 to 0.16. Whereas here the increase is from 0.13 to 0.24. It's almost doubled in our bead based columns, but here it's 1.5 times. See, I'm talking about the benefits, the construction of these columns helping you. So it helps you with retaining its sharpness, it helps you with better efficiency of ionization of the compounds. Altogether, it helps you getting better profile, consistent profile, whether it's a metabolite profile or proteomics profile. Now, here is the comparison of peak capacity in numbers. So see, this is our micropillar column. When you run 180-minute gradient, what is the peak capacity? Is 384. But in case of other packed column, it's around 265 to 300, because these are the two columns. They have of similar dimension, but different lots they have taken. And what we see is almost 33% better peak capacity with micropillar array columns. Now, what we are going to compare is the another case where we prepared the sample from Arabidopsis leaf metabolite, leaf extract, and we are looking at metabolite profile. What we see is the comparison. Here we have not compared between the two columns, but we compared that if I change the flow rates, what is the benefit? And if you see from zero point 0.9 microliter per minute, if I increase, if I decrease the flow rate to 0.3, that means 900 nanoliters per minute to 300 nanoliters per minute, the sensitivity of detection increased by 1.7 times. Consider it is two times higher sensitivity. So think about it. If your peak is looking like this, with a lower flow, your peak will be looking like this, isn't it? And when your peak is very close to noise, this flow rate, lower flow rate benefits you. It's close to noise, but when you reduce the flow rate, there is a better efficient ionization, and that peak is more intense. This intensity increases due to what? Due to better electrospray ionization and efficient ionization, which increases the response in the mass spectrometer. So it is present in this amount, but if you use optimum flow rate, you get better response. And see, when you see, look at the width at half height, right? The width, you are not compromising on width. It is 0.717 to 0.19. With decreasing the flow rate, slowing down your migration of your peaks doesn't impact to a very great extent. This is just test that you can consider 10% increase in the width. Not a huge, still very, very nice, very, very helpful. So when the base peak chromatograms of these Arabidopsis metabolite extract were compared between different gradient times, right? If you see the shorter gradient and the longer gradient, see this, they have improved they have used a longer gradient. So base peak chromatogram obtained for 420 minutes. See the gradient they are running for 420 minutes. How many hours is this? 7 hours. 7 hours one run. But what is the benefit? Benefit is you get identification of very low abundant compounds. And why it is so? Because in presence of high abundant compound, a lower abundant compound is getting an opportunity. Because in 420 minutes longer gradient, there is some separation. The moment there is a separation, and because you are running it at 300 nanoliters per minute flow rate, overall combination allows you to detect trace level of compounds in presence of high abundant compounds. So the benefit of higher run times provides you further increased in the detection and identification of low abundant compounds. So when we look at, when you run it for 180 minutes compared to that, when you look at 420 minutes, you'll be wondering what has happened to my width at half height. And see, it is 0.18. Okay, compare. And if when you go to here, when you go to 300-minute runtime or 420, it is moving from 0.18 to 0.24 to 0.27. Still much better. Peaks are becoming wider, as I said, but that provides you separation between small abundant compounds and big higher abundant compound. It allows better ionization because higher length of the higher uh, higher longer gradient time combined with lower flow rates provides you separation of compound followed by detection of trace amount of compounds. What you see on the left hand side are the different metabolites whose mass to charge ratios are given here, 408, 590. These are different metabolites. So it's not just like particular mass range, but mass range is covered from 400 to 800. And on different mass range, it is demonstrated that their retention time windows, their widths are consistent. This is applicable to all different type of molecules. So here we compare the peak capacity. Operating micropack nano LC column at their optimum flow rate. What is that? 0.3 microliter per minute. A substantial increase in peak capacity can be made with a very long gradient time. See, there is no point in running conventional columns at such a high flow rate because you don't gain anything. You do not gain anything. So therefore, they didn't run it. They run it only for 180 minutes with conventional column. And the flow rates were very high. We know that the flow rate was 300 microliters. This is what the gain was. At this gradient time, that is 180 minute, still this column, micropillar column, had an advantage. But when you further reduce, when you further increase the runtime at zero point 0.3 flow rate for micropack nano column, there is a huge gain in peak capacity. So 480 minutes, this is what you see. Okay. So in conclusion, the samples of high complexity can be separated using longer gradients. So you don't have to run separate samples. You don't have to separate low abundant compounds from with high abundant compounds. That can be done by running longer gradients. The purpose of running a longer gradient is to avoid the sample preparation and detect both low abundant compounds and high abundant compounds. A serious increase in detection sensitivity can be observed by combining columns with minimum peak dispersion and flow rate. So we saw that peak dispersion is the width. There is a minimum peak dispersion, and the flow rates are in the range of 200 to 300 nanoliters per minute. But it's a serious increase in detection sensitivity. Peak capacity values are almost can be taken to almost 2 times that of the state of the art UPLC column. I'm also always saying state of the art because this is the latest in the market, the best performers in the market. And increase in the peak capacity, if you see the samples on, so around 1.5 times increase in the peak capacity, which gave us 30% more identifications, right? So in conclusion, micropack column is already commercially available. They have generated application notes, and they have demonstrated that whether it's a metabolomics or proteomics, where you study in proteomics, you convert proteins into peptides, and you study peptides in proteomics. In both these cases, for different type of samples of biological importance, this is demonstrated. So with this, I conclude this session, and I would like to acknowledge my colleagues for their support in preparing these slides, helping me collect the data and present it to you. I thank you all for your kind attention and participation in this particular 2-day program. And I congratulate and thank the faculties at this particular college for making this particular arrangement, making all these participants to come across the latest technology in HPLC columns. Thank you very much. The forum is open for questions. So, madam, if you have list of questions, you can share with me. Yeah. Mhm. Okay. Mm. UHPLCMS. Okay. Okay.
And lucid presentation of the topic, sir. So maybe there will be questions once
Yeah.
people observe the presentations again. And
Yeah.
there have been requests from the participants and delegates that they would like to share, they want you to share the PPT with them so that they can have it as a reference. And in an event that they have any doubts or they want to understand it, they may be in touch with you. That's why, sir.
Sure.
Yeah.
So, what you can do is you can share their email addresses to us. We will send them the relevant material
Sure, sir.
so
Sure.
that they will get access to all the information which we presented.
Sure, sir. Sure, sure, sure.
Okay. So,
Yeah.
to all the participants, we will share with you the material we have, the application notes we have, which you can read and better understand. Rather than presentation, if you go through this application notes, you will better understand the presentation which I made. In presentation, you have a limitation of those slides, but in application note, you get to read all these concepts in a details. So I thank you all for your question, a particular question yesterday, today, and wish you all the best.
Thank you, sir. Thank you. We have had a wonderful session of 3 days where we have understood how micropack columns have revolutionized the whole system of separation efficiencies, column capacities, and the ability to identify the products, whether it is in proteomics or metabolites. And this is actually going to increase our urge to know more because once you have experienced small part of its, what you have shared with us is something like a tantalizing small part of it, which is going to help us going deeper into it. So the notes that you're going to share with us are definitely going to help us understand, explain, as well as implement more. So I really am thankful to Deepak sir and his team because they have extended a complete support and taken out time for us. And this system of interface between industry and education is extremely essential for both of them to go ahead and achieve success because both go hand in hand till we are able to imbibe each other's requirements and imbibe the qualities which are essential in science as a subject. And for that matter, chemistry is one which never gives up. It is a subject which has always tried to take on to what people have given us and then build upon it. As in case of chromatography, it is the credit goes to a botanist who gave us the beginning of it. And today, when we look at it, it's turned out into a wonderful analytical technique which has been brought up because of the contributions to chemistry. But at the same time, it is being used by a wide range of all the different departments, all the different branches of science. So, in total, it is again the future of science which is improving because we are trying to move into eco-friendly zones, trying to adopt systems and techniques which are going to help us achieve better results. I would now like to request Ms. Ashwina Patel to propose the vote of thanks.
Hello. Good afternoon, one and all. As quoted by our Honorable Prime Minister Sri Narendra Modi, I dream of a digital India where quality education reaches the most inaccessible corners driven by digital learning. Myself, Ashwina Patel, Assistant Professor of Chemistry at Srimati Devkiba Mohan Singh Ji Chauhan College of Commerce and Science, deem it a great honor to propose a vote of thanks in this memorable digital occasion. I, on behalf of our principal, professors, staff, technical team, and the entire college, extend a very hearty vote of thanks for our successful completion of today's webinar, that is Chromatography Multifaceted Analytical Technique. First of all, I would like to express my gratitude to our Honorable Chairman, Shri Fateh C.G. M. Chauhan sir, for always inspiring and supporting us to conduct such virtual sessions. Thank you, sir. I would also like to express my gratitude to our Secretary, Shri Devdas Shah sir, Treasurer, Shri Vishwesh Dave sir, and all managing committee members for their guidance and never-ending support. Thank you all. I would also like to express very special and heartfelt thanks to our distinguished speaker, Dr. Deepak Thakur, for sparing 2 days from his busy schedule and explain us all the importance of such an advanced technique that is not just used in the subject of chemistry but used in all disciplines of science in pharmaceutical industries and also biopharmaceutical industries. Thank you, sir. I would also like to express my gratitude to the principal of our college, Professor Dr. Ammadas Jadhav sir, for always motivating us to do our best and always to be positive. Thank you, sir. I thank all the people who have been the backbone of this event. The event coordinator and vice principal, Dr. Ramyoza, our IQAC coordinator, Mrs. Snehal Badgaonkar, our professors, staff, technical team for their immense cooperation to make this webinar a grand success. Finally, I would like to thank all our dear participants for joining us today. It has been a great pleasure and I hope you enjoyed this informative session. Thank you all once again. Kindly take a note that e-certificate will only be issued to those participants who have submitted the registration and feedback form. The feedback link form will be provided in the WhatsApp group and Telegram group within 1 hour after the completion of the webinar, and e-certificate will be provided within 7 days. Thank you all once again. I request all to please like and share our YouTube channel, Devkiba E-Knowledge Connect. Now I request Dr. Amioza ma'am to please end the webinar. Thank you. Principal sir, can you answer?
Thank you, Ashwina ma'am. Thank you very much. This has been a wonderful session, a wonderful 2 days understanding of the concept chromatography. Every time we look into the topic, we feel that we are learning something new. It's extremely enriching and enjoyable. The day we start enjoying the topic that we understand and teach, I think that spark becomes visible even in our students and even in us. It has been a great achievement for our college because it has completed its 14th national webinar today. And I thank Deepak sir for having helped us achieve this and all the members of ACRNS Technology. And I would like to thank all the participants waiting. You're joining us again when we organize one more national seminar, and expect your participation the way you have given us. This is Dr. Ami Oza from Dekiba College, Silvassa, signing off for today. Thank you, everyone. Thank you for your patience. Thank you for your participation. Thank you. Namaskar. Jai Hind.
Jai Hind. Thank you. Bye bye.
Thank you, sir.